Let's look a little bit more about expanding these binomials. Now, theoretically, this is what we're doing when we're expanding it out. 1 plus x to the power of n, we're getting 1 plus x, multiplied by 1 plus x, multiplied by 1 plus x, and so on and so on. So there's n of them there in the chain. Now, what we're really doing is we're choosing one item out of each of the parentheses and multiplying them together, and that will come up with a particular term. So in other words, I could, for instance, take x out of the first one, 1 out of the second one, x out of the next one, then 1, then 1, then 1, then 1, then 1, and then x out of the last one, and I would end up with x cubed. So the question is, how many different ways could I end up with x cubed? Or, using more language that we used back in our combinatorics exercises, how many different ways could I choose 3 x's from n sets of parentheses? And we'd say, oh, well, that's NC3. It's a combination because the order doesn't matter. I'm going to choose 3 from n. That's not a coincidence. That allows us to come up with a generalisation of the expansion where we don't actually need to use Pascal's triangle. Because what we know is the coefficient of x to the power of k will always be nck. I'm going to choose x out of k of the parentheses. Another way we sometimes write it when we're dealing with binomials is like this. So it's not a fraction, there's no vinculum there. We just put nk in parentheses. So if you see that notation, that's what they talk about. It's the same as saying nck. So 1 plus x to the power of n then, the expansion of it would be nc0 plus nc1x plus nc2x squared, and so on until we get to the last term, ncn x to the power of n. Of course, 1 and x limits us a bit, so let's generalise it even more, make it a and b, so we could have any expression we like. And so what we should see happening is the powers of a will start at n, and they will go down by 1. The powers of b, well, it starts at 0 and goes up by 1. The powers should always add up to b, whatever the power of the binomial expansion is. So now if I wanted to do 2 plus 3x to the power of 4, although that's not a hard one to remember the coefficients, but anyway, I could say, oh, well, I know that's going to be 4c0, 2 to the power of 4, 4c1, 2 cubed, power of 2 goes down by 1, but the power of 3x now goes up by 1, it's to the power of 1, and so on, and so on, and so on. And we can work out those binomial coefficients, and there's our answer, 16 plus 96x plus 216x squared, 216x cubed, and 81x to the power of 4. So let's go back to Pascal's triangle. 3 properties from that triangle that are quite important. nck equals n minus 1 ck minus 1 plus n minus 1 ck. That basically now is the rule from Pascal's triangle, which says to get any number, we add the 2 immediately above it. So nck, the one we're trying to find, well, the row above it would have been n minus 1, and we want to pick the nck and the one before that, because that'll be the 2 above it, and n minus 1 ck minus 1. So that's all that's really saying. Let's prove it. So 1 plus x to the power of n is equal to 1 plus x times 1 plus x to the power of n minus 1. So on the right-hand side, I've got 1 plus x plus now what I know the expansion to be. N minus 1 c0 plus n minus 1 c1x, and so on and so on. Now, if I'm only interested in the coefficient of x to the power of k, so on the left-hand side, that's just going to be nck, because that would be the expansion of the binomial. On the right-hand side, well, the 1 would be times the term with the x to the power of k, and the x would be times the term with the x to the k minus 1. And so we would get 1 times n minus 1 ck minus 1 plus 1 times n minus 1 ck, and that is indeed what we're trying to prove. So yes, it is true that nck is equal to those 2 things added together. This one here, nck will always equal ncn minus k. That's basically saying Pascal's triangle is symmetric. So if you look at any row, starts at 1 at each end, but then it goes in, and each time you go in, it's the same number. It's lovely and symmetric. And that kind of makes sense when you bring it back to combinatorics, because if I've got, let's say, 5c2, if I'm going to, how many ways can I choose 2 objects from 5, is exactly the same as how many ways can I choose 3 objects from 5. Because when I choose 2 objects from 5, That leaves 3 that I didn't choose, but there's the other group. So they will always be the same. And the third property there, that's just basically saying every row starts and finishes with 1. So NC0 will equal NCN will equal 1. Let's build on this expansion even more. Expanding perfect parentheses, these sorts of things, the perfect square, the perfect cubed and so on. Well, we know this one. A plus B squared is A squared plus 2AB plus B squared. But let's now think about it differently. A plus B squared. So my question is, what are all the different ways I could write down 2 pronumerals, but only using the pronumerals A and B? It's okay if they're the same. All right, I could get A squared, because I could choose A and A squared. I could choose B and B squared, and the other option is A and B, AB. Not interested in the order. Well, how many ways can you arrange 2 A's, or for that matter 2 B's? It's going to be the same answer. So that goes back to our combinatorics questions where we say, oh, all I got is the letters AA. How many words, or how many 2-letter words could you make from AA? Now, that's 1. Well, how many ways could you arrange 1A and 1B? AB or BA? There's 2 ways I could do that. Or more importantly, 2 factorial. So it's a rather strange way of coming up with the same thing, A squared plus 2AB plus B squared, but I'm more interested in the way of thinking about it rather than how we get it. Because we can push that idea through and generalise it. Doesn't matter if I only got A and B. What about if I had A plus B plus C plus however many you like? Okay, what are all the possibilities? I now know the answer has to be this. If I'm only using 2 pronumerals, I could have A squared or B squared or C squared or D squared or all the way up to N squared. All of those, there would be one way of arranging those 2 letters. But then I could have all the possible pairings, AB, AC, AN, BC, BN, CN. All the possible pairings are there. And there would be 2 ways of arranging that. So that would be the expansion for this one. But let's take it even further. What about our perfect cube? What are all the different ways of writing 3 pronumerals, but only using A and B? I could have 3 of the same pronumeral. So A cubed, or I could have B cubed. I could have 1 of one pronumeral and 2 of another pronumeral. So AB squared or A squared B. That pretty much covers all the possibilities. So the question now becomes, well, how many ways can I arrange these things? So how many ways could I arrange 3 A's or 3 B's? Well, one way of doing that. How many ways could I arrange 2 A's and 1 B? So 2 of one and 1 of the other. Well, think back to combinatorics. How many words could we make with A, and B? And we would have said, oh, that's 3 factorial over 2 factorial for the repetitions. And so we end up with our perfect cube. A cubed plus B cubed plus 3A squared B plus 3AB squared. Again, written in a different way, but it's the formula that we know. But that now allows me to do something like this. I can use the same idea. A plus B plus C cubed. How many ways? I'm only using A, B, or C. So I could have A cubed, I could have B cubed, I could have C cubed. I could have A squared B, A squared C, AB. So in that parentheses is all where I've chosen one letter twice and another letter. But this time we'll have yet another possibility, that being I just have one of all 3 letters. So I could have A, B, C. How many ways can I do these things? Well, it'd be one way for the A cubed or the B cubed or the C cubed. The A squared B was going to be exactly the same as we had before. There's 3 ways of doing that. So 3 factorial and 2 factorial. But that now brings me to A, B, C. How many ways can we arrange A, B, C? 3 objects, 3 factorial. So the expansion of A plus B plus C all cubed would be that. But why stop there? What about A plus B to the power of 4? So now, 2 pronumerals. Okay, I could have the same pronumeral 4 times. I could have 1 of one pronumeral, 3 of the other. I could also have 2 of one and 2 of the other. That pretty much covers everything with 4 pronumerals. How many ways can we arrange these things? Well, I had 4 A's. There's one way of doing it. 1A and 3 B's would be 4 factorial on 3 factorial. 2 A's and 2 B's would be 4 factorial on 2 factorial 2 factorial, which gives me the expansion for A plus B to the power of 4. But why stop there? How about if we want to expand A plus B plus C to the power of 4? So I've now got 3 pronumerals. I've got to have 4 using 3. What are all the different things that could happen? Well, yes, I could have A to the power of 4 plus B to the power of 4 plus C to the power of 4, and there would be one way of doing that. I could have 3 of one pronumeral and 1 of the other. There would be 4 factorial and 3 factorial ways of doing that. I could have 2 of one and then 1 of each of another 2. So ABC squared or AB squared C. How many ways of arranging that? Well, that would be 4 factorial on 2 factorial. Don't think I've got all of them yet. No, I could still have 2 of one, 2 of another. So that would be 4 factorial on 2 factorial, 2 factorial, giving me the expansion for A plus B plus C to the power of 4. Well, I'll stop there. So exercise 15b.